Have you ever wondered what the world is really made of? Not just what you see around you, but what lies beneath the surface, hidden from our eyes, waiting to be discovered? Imagine shrinking down with a super-powered magnifying glass, one that lets you see things 1,000,000 times smaller than a grain of sand. You look at your hand. At first, you see the ridges and lines of your skin. But zoom in, and you'll find skin cells, each one alive and bustling with activity. Go even deeper, and you'll see molecules, the tiny building blocks that make up everything you touch. Let's shrink past dust, past anything you can see, into a world where the rules are strange and the building blocks of everything are hidden. Here, things don't behave the way we expect. They can be in two places at once, or pop in and out of existence. This is the realm particle physicists explore, using giant machines called particle accelerators to smash tiny things together and see what's inside. These machines are some of the most complex ever built, stretching for miles underground. It's like smashing two clocks and studying the pieces to understand how they work, except the pieces are trillions of times smaller, and the clues they reveal help us unlock the secrets of the universe. As we shrink, atoms become vast landscapes, and what seems solid is actually mostly empty space, filled with buzzing, whirling particles that never stop moving. So put on your imaginary shrinking suit. We're diving past molecules, past atoms, into the very heart of matter, where the tiniest particles shape everything we know. We'll meet electrons, quarks, and a whole zoo of exotic particles, and see how they interact in ways that create the world around us. Each one plays a unique role in the cosmic dance of matter. This isn't just a story about tiny things, it's the story of everything. From you and me to the stars in the sky, and even the galaxies far beyond. Understanding the smallest things helps us understand the biggest mysteries, like how the universe began, and why it looks the way it does today. The journey to the smallest scale is one of science's greatest adventures. So, are you ready? Let's get started and see just how small we can go. The question, what is the smallest thing, has fascinated humans for thousands of years, sparking curiosity and debate across generations and cultures. In ancient Greece, the philosopher Democritus imagined taking a seashell and cutting it in half, then cutting the pieces again and again, over and over until you reached a fragment so tiny it could not be divided any further. He called this ultimate piece atomos, meaning indivisible. For centuries, this idea remained just a guess, a philosophical thought experiment with no way to prove it. But in the early 1800s, English scientist John Dalton revived the concept. He showed that elements always combined in simple whole number ratios, like tiny building blocks snapping together to form everything around us. Dalton pictured atoms as tiny, solid balls, each one unique to its element, like miniature marbles making up the world. But science didn't stop there. It kept pushing forward. In the late 1800s, J.J. Thomson's experiments revealed something astonishing. The electron, a tiny, negatively charged particle hidden inside the atom. Atoms weren't solid after all, they were made of even smaller parts with electrons swirling inside. Thomson imagined atoms as plum pudding, with electrons scattered like raisins in a blob of positive charge, a strange and new idea at the time. But then, Ernest Rutherford performed his famous gold foil experiment. He fired tiny particles at thin gold foil. Most passed straight through, but a few bounced back. Something dense and powerful was hidden inside. It was as if you fired a cannonball at tissue paper and against all odds, it bounced right back at you. Rutherford realized that atoms had a tiny, incredibly dense center, the nucleus, where most of the mass was concentrated. This experiment shattered the old plum pudding model and opened up a whole new world inside the atom, changing our understanding forever. The search for the smallest pieces was just beginning, as scientists now wondered what made up the nucleus itself. Each discovery led to deeper questions, pushing the boundaries of what we thought was possible. What else was hiding inside? The journey to find the tiniest building blocks of the universe was far from over. Rutherford's experiment revealed the atom's nucleus, a tiny, dense center with electrons orbiting far away. The atom was mostly empty space. Scientists soon found the nucleus contained protons, each with a positive charge. The number of protons made each element unique. But the nucleus was heavier than just protons. There had to be something else. In 1932, James Chadwick discovered the neutron, a neutral particle in the nucleus. Now the atom's picture was clear. A nucleus of protons and neutrons surrounded by electrons. For a while it seemed these were the fundamental building blocks. But physicists wondered, were protons and neutrons truly fundamental? They built powerful accelerators to smash protons and see what was inside. The results? Protons and neutrons weren't solid, they were made of even smaller things. The journey to the heart of matter was far from over. The universe was about to reveal another layer. Smashing protons and neutrons revealed a new family of particles, quarks. Murray Gell-Mann proposed that protons and neutrons are made of 3 quarks each. A proton, 2 up quarks and 1 down quark. A neutron, 1 up and 2 down. Quarks are so small they appear point-like, with no measurable size. There are 6 types or flavors of quarks: up, down, charm, strange, top and bottom. The heavier ones appear only in high-energy collisions. What about electrons? They belong to another family, leptons. Electrons, like quarks, seem truly fundamental, no smaller pieces inside. The lepton family includes the electron, muon, tau, and their ghostly partners, the neutrinos. So 2 main groups, quarks and leptons, the universe's bricks. But what holds them together? That's where bosons come in. Bosons are force carriers, photons for electromagnetism, gluons for the strong force. These particles are the mortar that binds the universe. Together, they build everything we see. With all these particles, physicists needed order. Enter the Standard Model, the ultimate rulebook for the tiny world. It organizes quarks, leptons, and bosons, and explains how they interact through 3 fundamental forces: electromagnetism, strong, and weak nuclear forces. The Standard Model is astonishingly accurate, tested in countless experiments. On one side, 12 matter particles, 6 quarks, 6 leptons. On the other, force-carrying bosons, photons, gluons, W and Z bosons. The Standard Model predicts how these particles behave and interact, but it's not the whole story. It leaves out gravity, the force we all experience daily. The Standard Model is a detailed map, but not the whole world. Some of the universe's biggest mysteries remain unsolved. The search for answers continues. Let's meet 2 of the most fascinating and mysterious particles in the universe: the elusive neutrino and the celebrated Higgs boson. These tiny entities play crucial roles in the fabric of reality, yet remain almost invisible to our daily lives. Neutrinos belong to the lepton family. They have almost no mass and carry no electric charge, making them incredibly difficult to detect. In fact, they interact so weakly with other matter that they can pass through entire planets without leaving a trace. Every second, trillions of neutrinos stream through your body, completely unnoticed and undisturbed. You are constantly bathed in a silent rain of these ghostly particles. Detecting them is a monumental challenge. Scientists build massive underground detectors, shielded from cosmic rays, hoping to catch just a handful of rare neutrino interactions each year. Neutrinos are messengers from the heart of the sun and from the universe's most energetic and violent events, like exploding stars and colliding galaxies. Now let's turn to the Higgs boson. For decades, physicists puzzled over a fundamental question: why do some particles have mass, while others do not? In the 1960s, Peter Higgs and other scientists proposed the existence of an invisible field, the Higgs field, that fills the entire universe everywhere and at all times. Particles gain mass by interacting with this field. Much like a celebrity moving through a crowded room is slowed down by the people around them. The more they interact, the heavier they become. The Higgs boson itself is a ripple, or a tiny disturbance in this all-pervasive field, a fleeting particle that proves the field's existence. For years, the Higgs boson was just a theory. But in 2012, after decades of searching, scientists at CERN's Large Hadron Collider finally detected it, confirming a major piece of our understanding of the universe. This monumental discovery completed the Standard Model's set of fundamental particles, like finding the last missing piece of a cosmic puzzle. The Higgs boson explains why matter has mass, allowing atoms, stars, and even life itself to exist. But even with these groundbreaking discoveries, many mysteries remain unsolved. There are still questions about dark matter, dark energy, and the true nature of the universe. The universe still holds secrets far beyond the Standard Model. The search for answers continues, pushing the boundaries of human knowledge ever further. The Standard Model is a triumph, but it's not the final answer. It explains 3 forces, but not gravity, the force that shapes planets and galaxies. We have general relativity for gravity on large scales, but it doesn't fit with quantum rules. Physicists dream of a theory that unites them, a quantum gravity theory. There's also dark matter galaxies spin too fast for visible matter alone, so something invisible must be holding them together. We call it dark matter, but we don't know what it is. None of the standard model's particles fit. And then there's dark energy, discovered when the universe's expansion was found to be speeding up. Dark energy acts like anti-gravity, pushing everything apart. Together, dark matter and dark energy make up 95% of the universe. The standard model explains only 5%, all the stars, planets, and people. The rest is a mystery, waiting to be solved. These gaps are not failures, they're invitations to explore. The adventure continues. Because the standard model can't answer everything, physicists are searching for a deeper theory. One bold idea is string theory. What if the smallest things aren't points, but tiny vibrating strings? Each vibration creates a different particle, like notes on a violin string. In this view, electrons, quarks, and photons are all different notes played by the same string. String theory could unite all forces, including gravity, by predicting a particle called the graviton. But it comes with wild ideas, like extra dimensions beyond the three we know. These extra dimensions are curled up, invisible to us. Other theories, like loop quantum gravity, offer different paths. Right now, these ideas are hard to test. Our experiments can't reach the required energies. We don't know if string theory is right, but it's an exciting frontier. Physicists are mapping new territory, driven by curiosity. The quest for a theory of everything is far from over. The universe may be stranger than we ever imagined. Our journey from atoms to quarks and beyond has been a wild ride. The standard model is a triumph, but mysteries like dark matter, dark energy, and quantum gravity remain. These are not dead ends. They're opportunities for discovery. What will we find next? New particles, extra dimensions, something even smaller? The search for the universe's building blocks is an ongoing adventure. Each generation pushes the boundaries further. The universe is vast and mysterious, and we've only just begun to explore. The next great discovery could be yours. The adventure is out there. Will you take up the challenge?